Hey everyone, and welcome to This Explainer. Today, we're pulling back the curtain on a microscopic reality show that's literally happening all around us, all the time. Forget human drama. We are zooming in on molecular drama. We're talking about atoms and elements constantly breaking up, swapping partners, and completely changing their identities. I promise, by the end of this, you are never going to look at a rusting nail or a burning candle the same way again. Okay, let's dive into this. Here is the menu for today's chemical reality show. First, the makeover. Then, the rules of the game. After that, romances and breakups, followed by the displacement drama, and we'll wrap it all up with understanding redox reactions. Let's get right into it. Section 1. The makeover. Physical versus chemical changes. So think of changes in matter kind of like a character transformation in a movie. A physical change, well, that's just a simple wardrobe change. If you melt ice or tear a piece of paper, sure, it looks different, but deep down, its core identity hasn't changed at all. It is still water, or it's still paper. A chemical change, on the other hand, is a fundamental personality shift. It entirely alters the chemical composition. Burning that paper or rusting a piece of iron creates a completely new substance. Now think about lighting a candle for a second. It's actually a brilliant example of both happening at the exact same time. The wax melting near the flame is just a physical change. It's just liquid wax now. But the wick actually burning and producing heat and light, that is a fundamental chemical change. Just like people have physical traits or tells when they're reacting to something, chemical reactions have these very distinct behavioral characteristics that let us know a true transformation has occurred. You might see a dramatic change in color. You might feel a sudden change in temperature, like it getting really hot, which is an exothermic reaction, or getting cold, an endothermic reaction. You might notice a change in state or the evolution of a gas, like sudden bubbling and fizzing out of nowhere. And sometimes a solid substance called a precipitate just magically forms out of two liquids. Basically, these are the visual clues that our molecular drama is officially underway. Moving right along to Section 2, the rules of the game, balancing chemical equations. In our chemical universe, before elements can interact and start all this drama, there has to be absolute perfect balance. So the crucial point is this quote right here, the law of conservation of mass. Mass can neither be created nor destroyed. This is an immutable law of the universe, and it is the exact reason why we absolutely must balance our chemical equations. In chemistry, you can't magically create a new atom out of thin air, and you definitely can't just make one vanish. Whatever goes into a reaction, the reactants, must perfectly equal whatever comes out, the products. I know balancing equations can sometimes seem like a really frustrating chore, but building a simple table actually turns it into a super satisfying logical puzzle. By just listing your elements, like iron, hydrogen, oxygen, and counting the atoms on the reactant side versus the product side, you can easily spot the imbalances. Like look at iron and oxygen here. They are completely out of whack. By systematically adding coefficients, multiplying the molecules on either side, you just adjust these numbers until the left perfectly matches the right. Honestly, it's exactly like solving a Sudoku puzzle. You just track your numbers in the grid until the whole shebang aligns perfectly. Oh, and before we leave the rules, we have to introduce a very special character, the catalyst. A catalyst is a substance that speeds up or slows down a chemical reaction without ever being consumed itself. Think of a catalyst like that one friend who instigates drama between a couple. They walk into the room, whisper a rumor, start a massive argument, and then somehow manage to walk away completely uninvolved and unchanged. That is exactly what a catalyst does in a chemical reaction. All right, Section 3, romances and breakups, combination and decomposition. Now here is where the relationship tropes of chemistry really shine, starting with atoms getting together and inevitably atoms falling apart. First up, we have combination, the romance. This is when two or more individual reactants come together to form one single unified product. For instance, if you take a strip of magnesium and burn it in the air, it reacts violently with oxygen. It burns with this dazzling, brilliant white flame to create a brand new single product, a white powder called magnesium oxide. But on the flip side, we have decomposition, the breakup. This is when a single compound is split apart into two or more separate products. But as we know, breakups rarely just happen on their own, right? They usually require some sort of external force, an energy trigger. And in chemistry, there are three main triggers for decomposition. First is thermal, or heat. If you heat green ferrous sulfate crystals, they break down, turning white and then a reddish-brown, releasing gas. Second is electrolytic, which uses electricity. You can actually pass an electric current through water to violently split it apart into hydrogen and oxygen gases. And third is photolytic, triggered by sunlight. For example, White silver chloride powder turns gray when you just leave it in the sun because the light energy physically breaks the silver apart from the chlorine. In fact, silver chloride's extreme sensitivity to light is exactly why it has to be stored in dark bottles in labs, and it's literally the core chemical reaction behind vintage black and white photography. Hey, if you're ever tested on that electrolytic breakup of water, here is a secret, highly energetic mnemonic trick to remember which gas goes exactly where. Say it with me, Chao Hat Oye. It roughly translates to move out of the way, but pay close attention to the letters here. C stands for cathode, where H, hydrogen gas, is collected. O stands for oxygen, which collects at A, the anode. It's absolutely foolproof. And a quick fun fact, if you test that collected hydrogen gas by bringing a flame near it, it's going to create a really distinct, loud pop sound. Let's move to section 4 and see how this builds. The displacement drama, stealing partners. So, let's explore these dramatic love triangles of the chemical world. To understand who steals whose partner, we have to consult the reactivity series. Elements at the top are incredibly powerful and reactive. Elements at the bottom are weak. A stronger element will always kick out a weaker element and steal its partner. To memorize this hierarchy, there's a brilliant mnemonic using car brands. It goes Katrina Nick Carmungi, Alto, Zen, Ferrari, Pirbihe Q Milli Silver Audi. It translates to Katrina asking for an Alto, Zen, or Ferrari, but why did she get a silver Audi? Notice how the first letters is perfectly mapped to the chemical symbols. K for potassium, Na for sodium, Ca for calcium, all the way down to Ag for silver and Au for gold. It's just a fantastic way to remember which elements hold all the power. And this brilliantly illustrates the concept in action. Imagine a beautiful blue solution of copper sulfate. Now, just drop a standard iron nail into it. Referencing our series, iron is much higher up than copper, so iron swoops in, actively kicks copper out of the compound, and takes its place. Visually, the drama is stunning. That blue solution slowly turns light green as it becomes iron sulfate, and the pure, displaced copper is left behind to form this reddish-brown crust entirely coating that iron nail. But hey, sometimes the exchange is totally mutual. Enter double displacement, the partner swap. This is when two different compounds completely exchange their ions to form two brand new compounds. Think of it kind of like fans of two rival sports teams meeting up after a game, peacefully swapping their jerseys and walking away happily in completely new outfits. Everyone wins. Now, a really cool thing about this double displacement partner swap is that it often leaves behind a massive visual clue, called a precipitate. A precipitate is an insoluble solid that just suddenly forms and settles at the bottom of a liquid solution. For instance, if you mix completely colorless lead nitrate with colorless potassium iodide, they swap partners, and instantly, like magic, a striking, bright yellow solid precipitate of lead iodide appears right there in the water. All right, finally, section 5, understanding redox reactions, the ultimate exchange. This is sort of the grand finale of our molecular drama, where two completely opposite actions happen at the exact same time. Let's define our terms first. Oxidation is simply when a substance gains oxygen during a reaction. Reduction is the exact opposite, when a substance loses oxygen. But here is the catch. In chemistry, these two processes almost never happen alone. If one thing is grabbing oxygen, it has to be taking it from somewhere else, right? When oxidation and reduction occur simultaneously in the same chemical equation, we combine the words and officially call it a redox reaction. Now, what's really interesting about this slide is the mental trick to solve the most confusing part of redox, identifying the agents. An agent is just the instigator. So if a substance brings about oxidation in something else, it's the oxidizing agent. The bulletproof trick to pass any chemistry test is the swiping trick. First, identify what got oxidized and what got reduced. Then just physically cross the terms. The substance that gets reduced is automatically the oxidizing agent. The substance that gets oxidized is automatically the reducing agent. Just swap them in your head and you will never, ever get it wrong. Which brings us to our final thought. The chemical drama of combination, decomposition, displacement, and redox isn't just something trapped inside a textbook or some sterile laboratory. It is literally the very fabric of our reality. So I want you to look around your room right now. Are your cells breaking down glucose for energy? Is a piece of metal slowly oxidizing near your window? The ultimate reality show is constantly unfolding right beside you at this exact moment. Thank you so much for joining me for this explainer, and keep your eyes open for the chemistry all around you.